One of the most important parts of any brush-based engine like Quake, Source, or even old versions of Unreal is the map compiler. This is the stage of the process where a level or map goes from a bunch of blocks in the editor to a final map with culling, lighting, optimizations, etc. We're going to dig deep into the technical aspects of how a map compiler truly functions by walking through the map compiler I've written for my own brush-based engine, Chisel. The goal behind map compilers is to take a simple, understandable version of the map that designers work with and edit, and turn it into a lit and optimized version ready to be played with in a game. There are many stages to the map compiler, but one of the most important ones is binary space partitioning. BSP is used through many different stages later on in the compiler, and in many cases inside the engine itself. It's also the stage that will set up the groundwork for the most important optimization stage, PVS. The Chisel map compiler specifically does a few things before BSP, such as generating basis vectors for faces and initializing some lookups, but that's not really what's important here. Before continuing any further down the pipeline, let's build intuition for what brushes are. Brushes are a collection of planes. A plane is an infinitely large face defined by a normal and the distance from the origin along that normal. The geometry of a brush is the volume behind all of its planes. In 2 dimensions, we can represent a plane as a line, and I'll add an arrow to display directionality. We can see having a few lines that all point outward, we create this inner space. That is the actual brush geometry. The same idea applies in 3 dimensions. This volume defined by the planes is necessarily always convex. There is no configuration of planes that can produce a self-intersecting shape, which does make quite a lot of things easier down the line. These brushes are the building block, literally, of a map, and we'll go more over how we can actually create meshes from them when we talk about PVS. For now, though, it's enough to understand that each face of a brush also has a corresponding plane. To begin, we'll use a simple test map for demonstration. The first step is collecting all of the unique planes in the map. To collect these planes, we'll loop over all of the faces of all of the brushes and track their respective plane. Importantly, though, we can't have duplicate planes. We need to have a function that will detect identical or mirrored planes and merge them into one. Otherwise, we'll have a lot of problems in later optimization steps with infinitely thin leaves of the BSP tree. To do this, we'll instead pass these into this findPlane function. FindPlane will first normalize the plane, which will return the same value for a given plane and its mirror image. We check to find the most dominant axis of this plane, and if that dominant axis is negative, then it will be flipped. This ensures that a plane and a flipped version of that same plane will both normalize to the same value. After that, we check all other planes that we've kept track of so far, and only if this new plane is too unlike all other planes do we add it to the list. Otherwise, we just return the existing similar plane. Back where we call findPlane on every brush face, we want to store the found plane in a list of splits. Importantly, we store the plane in our list of splits even if it is a duplicate plane. Later on, it'll be important to keep track of it even though it's a duplicate. With this plane, we'll also track the brush and face that it came from. An optional step before creating the BSP tree is sorting the splitting planes that we've accumulated. Some orders of cuts will produce more optimal results than others. So, the Chisel map compiler specifically orders them by the approximate size of the face they originate from, such that larger faces get added first. This isn't strictly necessary, but the right sorting function can improve the tree's complexity quite a bit, and I suspect Source and Quake do a very similar thing. Finally, we have a complete set of all of the splits we want to make to the BSP tree, though let's not forget that we're still storing duplicate planes as well. Why exactly will be evident soon. Nevertheless, let's dive into BSP. Each node of the BSP tree has a splitting plane, and an array of brushes that are contained on the back side of that node, that is, the side opposite the normal. The tree is arranged in such a way that any point query can be solved by traversing down the nodes of the tree, and at each node, deciding to walk left or right by determining which side of that node's splitting plane we are on, recursively until we are down to a leaf node, that is, a node with no children. We now have a set of planes, as well as the brushes and faces that they came from, and now we need to create this BSP tree from this set. For each split that we want to make, we'll walk the current tree down, following every path. If we hit a leaf node, which we will on the first iteration of course, then we want to split that node. A split is only performed on a node if the brush that the split came from is contained within the node itself. We'll set the leaf's splitting plane to the current plane that we're iterating over. Then we'll add 2 new leaf nodes, and divvy out the brushes that are contained within the parent to the children, based on whether they are on the front or back side of this splitting plane. Brushes that cover both are added to the front and the back. On the next iteration, we'll have to actually walk down another level. If our search for a node to cut lands us on a non-leaf node, then we'll add the 2 children nodes to that search. Importantly, though, this is where we're going to check for a duplicate plane. Remember that, while find plane gave us existing planes where it could, we intentionally stored any copies of a plane. We'll take advantage of that now, and if the plane we're trying to split with is close enough to the plane of the current non-leaf node, we will instead add the brush that the split came from to the proper children and skip clipping the children for that node. This way, the brushes go where they're supposed to, and we avoid creating identical splits and causing trouble during later stages of compilation. We repeat this simple loop, looking at each node, checking if it's a leaf or not, cutting leaf nodes, and adding brushes to existing nodes when necessary until all of our splits have been processed. When all of our splits have been done, each leaf node will either represent an empty or solid volume of space, and to classify which is which, we can simply iterate over every node and call it solid if its contents are greater than 0, and empty otherwise. We have now created a BSP representation of our entire map, where we can run ray tests, point queries, and all manner of other things in a very swift and efficient manner. BSP is one of the most important stages. It makes it performant to perform our lighting calculations. It's a necessary step for the PVS occlusion system, and it even makes simple ray tests like bullet versus map geometry much faster in Elgen as well. In the map compiler, though, all brush entities are skipped for the BSP building stage and cast shadows on the light map by a more typical BVH system, same as the models placed in the editor. But either way, the BSP tree saves a lot of time and is a vital component of the brush-based architecture. Next time, we'll go over the PVS occlusion system, which will talk a bit more about the BSP tree. Until then, though, consider supporting the channel by subscribing, commenting, or tossing a dime over on Patreon or via the channel memberships. If you care to learn more about my engine, Chisel, feel free to follow the series that documents its development, linked here.